All right, guys, let's continue. That's the last section from this chapter. Again, substitution and area between curves. In the previous session, we talked about indefinite integrals and the substitution method. And now we are going to use this method to do, what is it, to evaluate definite integrals. And also we have one small theorem here. And also we'll practice how to find the area between two curves. And the curves are just the graphs of two functions. Okay, what we have here, we have substitution formula, definite integrals of symmetric functions, areas between curves, and integration with respect to y. So there are two methods for evaluating a definite integral by substitution. One method is to find an antiderivative using substitution, and then to evaluate the definite integral by applying the evaluation theorem. The other method extends the process of substitution directed to definite integrals by changing the limits of integration. So we will use a new formula that we introduce here to compute the area between two curves. Anyway, so here, actually, there's not a big difference, okay? In evaluating, you will see that and sometimes first you evaluate this, okay, using the original variable, or if you don't want to use the original variable, you can introduce a new variable, and also you have to change the integration limits, and after that evaluate this, and after this, what is it? I think that's it. Okay. Anyway, let's start with this formula or the theorem. Okay, we have already done this. It's very similar to the theorem that we have seen in the previous session, right? But here the difference is that is a definite integral. That means that the integral has limits. So it says that if g prime is continuous on AB, and why we are saying that g prime is continuous, because when you're defining an integral, right, the function must be continuous or piecewise continuous. Otherwise, it may be troublesome, or we may not be able to integrate this. If g prime is continuous, because see here inside this integral we have g prime, that's why we need this condition on a closed interval AB, and the function f is continuous on the range of g of x equals u. Why? Because if you look at this function f here, it is input values are the output values of g function, right? And that's why we are saying that on the range of g of x. Then this integral is equal to, what is it? Integral from g of a to g of b, f of u to f u. And how we are doing this one, again, you'll in examples, you'll understand much better, because here, if you introduce this g of x, for example, if I introduce this variable, u is equal to g of x, right? So at the time, what do we have here? Let me just write the integral here. We have f. What is g of x? It is u. And what is g prime of x? dx, right? I can just bring this inside. So that is du, right? Now, how about this integration limits? Actually, what is the value of u when x is equal to a? So actually, u is equal to g of a, right? And also here we have u is equal to g of b. And since these two functions are continuous, right? If you're making this substitution, and what is it? And also it takes all the values between g of a and g of b. And that's why also we have to change the integration limits here. Here we have g of a, and here we have g of b. Okay, and this is how we evaluate this kind of integrals. Of course, here, this method, when we should use this method, if our function is in this form. You know, first you have to check this. Is it in this form or not? Because most of the time you can write the function given here as an integral. You can write it as a function f, okay, and here a function of g, and times g prime of x. So if the function is in this form at the time, we can use this method. Let's see one example. Maybe you can use both methods, or maybe one of them, I don't know. We will see, okay? Because every time I don't want to show everything, just we need to focus on one thing so they can understand much better. In this question, is 3x squared and x cubed plus 1. If I introduce this variable, u is equal to x cubed plus 1, right? So now from here, what is the differential of u? Differential of u is equal to 3x squared, and here we have dx. Okay, this 3x squared with this function part, we are done. And how about the integration limits, right? Because here x is changing from -1 to 1. So if x is changing from -1 to 1, how this u changes? So now if you evaluate this, when x is equal to -1, that is lower limits, right? That's equal to, what is the value of u -1? That's equal to -1 cubed plus 1, that's equal to 0. And how about if x is equal to 1, upper limit, that is u of 1, that's equal to 1 cubed plus 1, that's equal to 2. So at that time, this integral, let's say I, and here we have integral I becomes integral. Now I'm going to write everything in terms of u. So u is changing from 0 to 2. And what is this x cubed plus 1? X cubed plus 1 is u. So here we have square root of u. And how about this 3x squared dx? That's equal to du, right? So here we have du, which is equal to, now we have to evaluate this integral. That's equal to integral from 0 to 2, u to the power of 1 over 2 du, which is equal to u to the power of 1 over 2 plus 1, that is 3 over 2. Now here we have 2 over 3 from 0 to 2. When u is equal to 0, that's equal to 2. When it is 2, so that thing is equal to 2 over 3 times 2 to the power of 3 over 2, which is equal to square root of 8, right? That is 2 times square root of 2. So that is 4 times square root of 2 over 3. So this definite integral is equal to 4 times square root of 2 over 3. And how about the second method? Actually, at the beginning, we see that usually we use two different methods. Not very different, actually, they're so similar to each other. Okay. So, what is it? The second one is you're not making this substitution. Okay. Immediately, you can just write it as, for example, I can just write it as integral from -1 to 1. So here we have 3x cubed plus 1. And here we have d 3x, sorry, it's not 3, right? Just here we have x cubed plus 1, and here d x cubed plus 1. Okay, and just consider this x cubed plus 1 a u in your mind. Okay, then evaluate this, so you don't have to change this integration limits. But usually this changing the integration limits and using this new variable, that is more practical. Another example, calculate or evaluate the definite integral by using the method of transforming the limits of integration. So that means that we are talking about the previous method, solution, okay, between pi over 4 and the pi over 2. Actually, cotangent is cosine over sine. We have no problem. And cosecant is 1 over sine. Also no problem. Okay. So now we know that this cotangent of theta, a cosecant squared of theta, right? So that's equal to, let me just rewrite first. Here we have cotangent of theta. This cosecant squared of theta, we can write it as cosecant of theta times cosecant of theta. And here we have d theta, right? Actually, what function's derivative is cosecant? Actually, here we have, we know that if you differentiate this, what is it? D cosecant of theta, right, is equal to what? That's equal to minus cotangent of theta times what is it? Cotangent of theta, cosecant of theta, and that's equal to d theta. Okay, so now instead of this one, right, I can just write minus d cosecant of theta. So that's equal to minus, and here we have, so we have cosecant of theta, and here we have d theta. I'll make this substitution. That's the first one. And how about actually if I need to have cosecant, right? Cosecant of theta. So that's the first one. And the second one is suppose that u is equal to cosecant of theta. Okay. Now from here, if actually theta is equal to pi over 4, theta is equal to pi over 4, then cosecant of theta is equal to 1 over square root of 2, right? That's equal to square root of 2. And how about theta is equal to pi over 2 as a time cosecant of theta? That's equal to 1 over cosine. 1 over cosine is equal to 0. There's a problem here. I have this. No, cosecant. Cosecant is sine, right? That's equal to 1. It's not cosine, sorry. So that's equal to 1. Okay. So now I will make this substitution here. So let's say this integral is I. At that time, this I becomes integral. And here we have pi over 4. That is square root of 2. And here we have 1. And what is cotangent of theta times cosecant square root of theta d theta? The whole thing is equal to, what is it? Minus, let me keep minus here. Here we have u du, right? So here now it gets very simple form. So which is equal to minus u squared over 2. Here we have integration limits from square root of 2 to 1. So here we have minus 1 over 2. When it is 1 is equal to 1. When is when u is equal to square root of 2, that's equal to 2. So the answer is 1 over 2. Okay. Now we have one theorem here. Sometimes it helps us to, how to say, simplify our calculation. Okay, just cut it in half, or sometimes even without doing any evaluation calculation, you can see get the answer if our function is symmetric. Okay, so number 1. Different integrals of symmetric functions. Let f be a continuous on the symmetric interval, or continuous function on the symmetric interval negative a and a. As see here, the integral of integration must be symmetric about the origin, that is from minus a to a. If f is even, then integral from minus a to a f of x dx is equal to 2 times integral from 0 to a f of x dx. If f is an odd function, then integral from minus a to a f of x dx is equal to 0. Especially the second one, if our function is an odd function, okay? So you don't have to evaluate this immediately, that's equal to 0. Why is it so? Proof is also simple, not complicated. We are just going to use the idea of this substitution, okay? Let's start with the first part. Use, okay, part A. It says that if f is even function, if you remember the definition of even function, what is it? That is f of minus x is equal to f of x. Okay, it means this. So now to evaluate this integral, let's say a is equal to integral from minus a to a. And here we have f of x and dx. And by using the property of the integral, I can just divide this into 2. I can just evaluate this as minus a to 0. Here we have f of x dx plus integral from 0 to a and f of x dx. Okay. So now the first one, I can interchange this. If we interchange this, also we have to put minus, right? If we interchange the integration limits, so here we have minus integral from 0 to negative a. So here we have f of x and the dx plus integral from 0 to a and f of x and the dx. Okay, now this part, actually the first part from 0 to minus a, okay, f of x dx. So if we introduce this for this part, okay, for this part, I will introduce this variable. Let's say u is equal to minus x. Okay, so at that time, this du becomes minus dx, number one. And how about integration limits? If x is equal to 0, u is equal to 0, right? And if x is equal to minus a, u is equal to a. So considering this one, okay, I'm just going to evaluate the second part only. So if you evaluate the second part, you will see it will be this exactly the same with the second, the first part, the second part, right? So the first part is minus integral from 0 to minus a f of x and the dx. And since I'm making this substitution, right, that means that x is equal to minus u. So here we have minus, and the u is equal to x. When x equals 0, u is equal to 0. So that's equal to 0. And when x equals minus a, u is equal to a. So here we have a. And here we have f of, what is x? X is equal to minus u. And how about dx? Dx is equal to minus du. So minus, let me just put minus here, du, which is equal to minus minus, it is plus, and from integral from 0 to a, and f of minus here, because it's even function, that's why here we have f of u and du. That means that actually I can write u du or x dx or w dn, it doesn't matter. See here, these two things are exactly the same. And that's why it's just equal to 2 times integral from 0 to a f of x dx. In similar way, if it is odd, you will see that the two things, it will be the same, but one is with minus. That's why if you add them, you will get 0. And also if you look at bigger graphs, right? For example, the first one is the graph of an even function, which is symmetric about the y-axis. And that's why these actual areas are also symmetric and both are lying about either above the x-axis or below the x-axis. That's why just evaluate one part of the area, one half of this area, and multiply this by 2. And the second one, see here the blue part and blue part, right? Brown part and brown part. Since it is odd function, and if you're integrating this function over the symmetric interval, then that's why the sum will be 0. All right. Now let's just use them. Evaluate the following integrals. The first one, minus 2 to 2, right? Integral from negative 2 to 2, x to the power of 4 minus 4x squared plus 6. As you see here, the integrand function, right? It is an even function. So we don't have to evaluate this from negative 2 to 2. So that's just equal to 2 times integral from 0 to 2. And here we have x to the power of 4 minus 4x squared plus 6. And here we have dx, or which is equal to 2 x to the power of 4, that is x to the power of 5 over 5, minus 4 over 3 x cubed, plus and 6, that is just 6x from 0 to 2, which is equal to 2 times, one it is 0, everything is 0 because every term contains x, one it is 2, 2 to the power of 5, that is 32 over 5, minus, and here we have 8, that is 2 cubed is 8, 4 times 8, 32, again 32 over 3, plus 6 times 2, that's equal to 12. Okay, so now we can just evaluate this. If you evaluate this, that will also just write the final answer. So we have 2 times, okay, 32 over 5 minus 32 over 3 plus 12, which is equal to, which is equal to 15 and 7 over 15. Okay, that is the answer. And how about the second one? As see here, the integration limits from negative 3 to 3. It is symmetric about the origin, and also x to the power of 5 minus 4x cubed, right? It is an odd function. And that's why this just integral is equal to 0. We don't have to evaluate this. Okay. Areas between curves. If f and g are continuous with f is greater than or equal to g throughout the closed interval AB, then the area of the region between the curves y equals f and y equals g from A to B is the integral of f minus g, and from A to B. Why is this so? Because if you look at the first figure, and since in the question we are saying that it's our condition, f is greater than or equal to g over this interval, closed interval AB. That means that maybe at the point they may intersect each other, but actually this f is lying above the g, right? And suppose that that blue line is the graph of the function f, this orange line is the graph of the function g. Okay, so the question is, how do we differentiate the region which is bounded by these two curves and the vertical lines x equals a and x equals b, right? And to do this one again, we are just going to, what is it, form first our Riemann sum. To do this one, we have to partition this interval AB into, or divide this into n subintervals, right? So here we have x sub 0, x1, x2, x3, blah, 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 until xn. And after that, we are going to approximate the area of each rectangle, right? If we just pick one of them, here, this is the third figure, right? So that is see here, the height of this rectangle will be the difference of these two functions. Because if you know that if horizontal line or vertical line, it doesn't matter. If you're given 2 points, let's say this one is y1 and this one is y2. And what is the distance between these 2 points? If I know that y1 is greater than or equal to y3, 0, then distance will be equal to y1 minus y0. If I don't know which one is greater, at that time we will put absolute value signs. But here we know that actually y1 is greater, so that's why y1 is minus y0. That's why in the condition we are saying that if f is greater than or equal to g throughout AB, at the time if we just take its difference, it gives us the height of this particular rectangle. And how about its width? Its width is just delta x. And that's why if we just collect them all, it gives us in this definite integral where that is f minus g. Okay, now let's use this, what is it, formula to solve this question. Find the area of the region enclosed by the parabola y is equal to 2 minus x squared, and the line y is equal to minus x. So here, let's say this one is our y-axis and the x-axis. y2 minus x squared, right? The graph of this parabola is, let's say this one is minus square root of 2, and this will be square root of 2. And this one is 2, okay? Because it looks up, downward, right? So its graph is something like this. Okay, that's the graph of this parabola. And how about y equals minus x? Y equals minus x is, it is just identity function. It will be like this. Okay, all right. So the question is, what is the area, right, of the region enclosed by the parabola in this line? So we are looking for the area of this region. We're going to find this. Okay. So number one, I know that actually this 2 minus x squared, our first function, is lying above the second function, that's y equals minus x. Okay, I got it. And how about the integration limits? To find the integration limits, right, we have to find the intersection points. That is A, let me just write here A, and this one is, what is it? It is B. Okay, it is B. And to find the value of A and B, right, to find the intersection points, we have to solve the equation. What is it? That is 2 minus x squared is equal to minus x. Or take everything or move everything to the right hand side. X squared minus x minus 2 is equal to 0. It's just a quarterly function, factorize it. It is x minus 2 and x plus 1 is equal to 0. Okay, so minus 2, that's correct. So that means that A is equal to -1 and B is equal to 2. That's the first part. And that is a bit challenging part, especially solving questions. Now I have to evaluate this. To evaluate this one, the second part, so the area of the shaded region is equal to definite integral from -1 to 2. And here we have f minus g. What is our f? F is 2 minus x squared. Minus, and how about g? That is minus x. And here we have dx. Or that's equal to integral minus 1 to 2. Here we have minus x squared plus x plus 2 dx. So which is equal to the minus x squared, that is minus x cubed over 3, plus second one is x squared over 2, and third term is 2x, and it's changing from -1 to 2. So when it is 2, that is minus 8 over 3 plus 4 over 2, that is 2, and 2 times 2, that is 4. Minus, when it's -1, here we have 1 over 3, 1 over 3, and the 1 over 2 minus 2, right? That's equal to just minus 3 over 2, minus 3 over 2, which is equal to, here we have 6, 18, 18 minus 8, so that's equal to 10 over 3, minus, and 2 minus 9, minus 7, so this plus 7 over 6. That's equal to 20, 27 over 6, or by 3, 9 over 2. So the area of the region, which is enclosed by these two curves, is equal to 9 over 2. Another example, find the area of the region in the first quadrant that is bounded above by y equals square root of x and below by the x-axis and the line y equals x squared. Solution. Okay, the first quadrant, I just need only the first quadrant. Okay, so y-axis, this one is x-axis. And what is the graph of this y equals square root of x? It is something like this. And how about x minus 2? When x is equal to 2 is equal to 0, right? And we just write here, this one is 2, and this one is 4, and actually when it is 4, the value of the first function is equal to 2, because square root of x, right? So when do they intersect each other? At 4, because at 4, the square root of x is equal to x minus 2. If you solve this in the first quadrant, when do they intersect each other? They intersect each other when x is equal to 4. So actually they intersect each other when x equals 4. Okay. So now again, we have to find this region. Right? We have to find the area of this region. Okay. All right. One way to do this one is, actually, I can just extend this line, okay, in this direction. And also I can extend this line until here, okay. I can evaluate this from 0 to 4 and subtract this triangular part because it is 2. And when actually it crosses the y-axis, when x equals 0, this point is -2, okay. What is this area? This area is equal to 1 over 2, okay. And another method is maybe I should just divide this into 2 parts and evaluate this, okay? But here I prefer to use this method, okay? Because if you evaluate this, what is the area of the shaded region? That's equal to integral from 0 to 4, okay? So 0 to 4, that is square root of x minus, the second function is x minus 2 and dx. So it gives us the whole figure, right? Let me just write here the name. This one is O, and this part, let's say this P, and this one is Q. Okay, let me just write here also this one is P, and I say this Q. So it actually gives us the area of, what is it, OPQ. But actually this triangular part is not included, so I have to remove it. So minus 1 over 2 times 2 times 2. That's the area of this triangle. Okay, then we get the shaded region, which is equal to, now the first part is x to the power of 1 over 2. So here we have x to the power of 1 over 2, that's 3 over 2. And here we have 2 over 3 minus x, that is x squared over 2, plus here we have 2, that is 2x. Definite integral, right? Integration limits are from 0 to 4. Minus, and here we have 2. When it is 0, that's equal to 0. When it is 4, here we have 2 over 3 times square root of 2 is 4. 4 is 2, 2 cubed, that is 8. Minus 4 squared is 16 over 2, that is 8. Plus, and here we have 8. And minus 2. Minus 8 plus 8 is equal to 0. 16 over 3. 16 over 3 minus 2, which is equal to 10 over 3. That is the area of the shaded region in the first quadrant, which is bounded by the curve y equals square root of x and the function y equals x minus 2 and the x-axis. Integration with respect to y. But here just actually the role of x and y, the interchange, okay? And if we just rotate this 90 degrees to the left or to the right, you'll see it's just the same thing. But sometimes instead of this x and y, if you get confused, just change them. You will understand this more clearly. Anyway, if you're integrating a region with respect to y, how do we do that? Actually, at the time, our rectangles, with the small rectangles, they will not be vertical ones. They will be horizontal ones. And suppose that here we are given a function and a region which is bounded by the graphs of two functions, that is x equals g of y and x equals f of y. Okay, and which is bounded by the horizontal lines, y is equal to b and y is equal to c. So now if we just partition this like this with the small rectangles, as you see here, the length of the rectangle, its width will be dy. Actually, its width is dy, right? That's the width of the rectangle, that's delta y. And how about it is length? Again, in horizontal line, if you're given 2 points, let's say this one is x1 and this point is x2. And how do you find the distance between these 2 points? The distance, if I know that x2 is to the right of x1, so that's equal to x2 minus x1. And that's why here we have f of y, which is to the right of this function, right? Minus g of y dy. Okay. Example, find the area between the curves x equals y squared and x equals y plus 6. Of course, also I can change this. Actually, I can express y in terms of x, and after that evaluate this. Since we're just going to practice something different, that's why I'm going to evaluate this like as it is given. So this one, let's say this y, and this one is x. Even when you're drawing, actually, you can just draw it as y. For example, let's say, how about if this one is x, this one is y, okay? So x equals y squared. So actually it is this parabola, right? It will be this parabola. And how about x equals y plus 6? That means y equals x plus 6. When x is equal to 0, it is 0, right? When x equals something, I don't know, actually, if x equals minus 6, okay. If minus 6, x is equal to 0, right? Okay, minus 6. Okay, minus 6. Just draw like this. Okay, it is something like this. Okay. So we are talking about this region. Okay, so now we have to find their intersection point. This one is y1 and this one is y2. Okay, to do this one, we have to solve this equation. Y squared is equal to y plus 6. Or y squared minus y minus 6 is equal to 0. So from here, y minus 3 and y plus 2 is equal to 0. Now from here, what is y1? y1 is equal to negative 2. And y2 is equal to 3. It is 2 bright. So now at the time, this area will be equal to integral from y1 to y2, that is from negative 2 to 3, right? And the function of the straight line, that is y plus 6, that is y plus 6 minus the parabola, that is y squared. And here we have dy. And of course, if you just write this vertical line as y at the time, it will be a bit different, but the idea is similar. So now if you integrate this, that is 1 over 2 y squared plus 6y minus 1 over 3 y cubed from negative 2 to 3, which is equal to, if it is 3, so here we have 9 over 2 plus 18 minus, and here we have 9 minus, if it is negative 2, negative 2 square 4 over 2, that is 2 minus 12, and plus, it is 8 over 3, which is equal to, for let's just simplify the whole numbers, 18 minus 9, it is 9, and then minus 10 plus 10, so here we have 19, plus 9 over 2 minus 8 over 3, which is equal to 19 plus, here we have 6, 27, 16, 11, right? So that is 19, extra 20, it is 20, and 5 over 6. Okay, guys, that's all for today. Tomorrow, I will see, maybe I'll do some revision, okay? And after that, Wednesday, we will continue with new lesson. Thank you very much. Have a good day. I'll see you tomorrow. Thank you. Bye-bye.
Goodbye, sir.
Bye-bye. Thank you.